Okay, let me start it. Today we are going to discuss sampling, the concept of sampling. So before going to discuss this concept, first I have to discuss some basics. So first I quickly go through the basics and then I'll come back. Okay. So first I require the impulse signal. Impulse signal represented with del of t. So del of t equal to infinity at t equal to 0 and 0 for t not equal to 0 and integral minus infinity to plus infinity del of t dt equal to 1. So this is the definition of impulse signal. Okay, and the properties of del of t. First one, x of t into del of t equal to x of 0 into del of t. So del of t has value at t equal to 0 only. Otherwise, del of t has 0 at t not equal to 0. X of t into del of t minus t naught equal to x of t naught into del of t minus t naught. And this del of t minus t naught has value at t equal to t naught. T minus t naught equal to 0. It is at t equal to t naught. Okay. Next, x of t convolution with del of t. I will get x of t. X of t convolution with del of t minus t naught. X of t minus t naught. So del of at 1 by mod a del of t. Yeah, these are sufficient for me to discuss our sampling concept. And one more concept. And first of all, what is meant by delta function? This del of t. So if I represent some a times del of t, this a is not amplitude of del of t. Okay, it is area. Actually, area of del of t. Why? It has value at t equal to 0 is infinity. Okay, infinity multiplied by a is infinity at t equal to 0. So del of t has no information. Why? It has this is del of t. At t equal to 0, it has value infinity, but area should be equal to 1 for unit impulse. If I represent a into del of t, it has area is a. Okay, not amplitude. Amplitude always infinity at t equal to 0. Why it is area? Because integral over minus infinity to plus infinity a times del of t dt equal to what you get, a into integral minus infinity plus infinity del of t. It is a. This value is 1. So what does it mean? Integral over some signal is nothing but area. So what you got? Area only. A. That A is area. Okay. It is not amplitude. It is area. That is important. Okay. Now I am going to discuss the Fourier series coefficient of impulse train that is required for me to discuss sampling signal, sampling concept. So I will take impulse train in time domain. Let us say P of t. Okay. 0. Let us say Ts, 2Ts, 3Ts, and so on. Minus Ts, minus 2Ts, and so on. Let us say this value is 1. So this is called impulse train. It has period equal to Ts. Okay. So I want to find out its Fourier series coefficient. Continuous time Fourier series coefficient. Because P of t is a periodic with a period Ts, it has Fourier series representation. So P of t has, let us say, Fourier series representation Ck, that equal to 1 by period minus Ts by 2 to plus Ts by 2. Signal is P of t into e power minus j k omega naught equal to 2 pi by Ts into t to dt. Okay. This is Fourier series coefficient. In fact, exponential Fourier series coefficient. Okay. So that equal to 1 over Ts integral of minus Ts by 2 to plus Ts by 2. What is P of t? At minus Ts by 2 to plus Ts by 2. These points are minus Ts by 2 plus Ts by 2. What is the signal present between minus Ts by 2 to plus Ts by 2? We have del of t. So P of t is del of t. E power minus j k times of 2 pi by Ts into t to dt. Here 1 over Ts integral of minus Ts by 2 to plus Ts by 2. X of t, let us say this is some x of t into del of t, the x of 0. So del of t into e power minus j k 2 pi by Ts into 0 to dt. So that value is 1 over Ts minus Ts by 2 to plus Ts by 2 del of t dt. And remember, minus Ts, the t limits are minus Ts by 2 to plus Ts by 2. So the t limits are minus Ts by 2 to plus Ts by 2. So in between we have 0. Minus Ts by 2, minus Ts by 2 to plus Ts by 2. So we have 0. So 0 is there. So if limit contain 0, then we will get area under this curve become 1. Area under impulse, unit impulse is 1. If 0 include in the limits, otherwise it is 0. So that is Ts. So exponential Fourier series coefficient is Ck, that is 1 by Ts. Then how you represent? Once you got Ck, so that's P of t equal to sigma k equal to minus infinity to plus infinity Ck e power plus j k k 2 pi by Ts k times of omega naught t. Omega naught is 2 pi by Ts into t. This is P of t. So we got P of t equal to Ck equal to 1 by Ts sigma k equal to minus infinity to plus infinity 1 by Ts e power j k times of 2 pi by Ts into t. This is P of t. So remember, in this term you should always remember P of t. And I want continuous time Fourier transform of P of t. Okay. So just apply Fourier transform on both sides. Let's say P of omega sigma k equal to minus infinity to plus infinity 1 by Ts e power j omega naught t has Fourier transform 2 pi del of omega minus omega naught, where omega naught is k times of 2 pi by Ts. K times of 2 pi by Ts. Okay. Let us say this 2 pi by Ts as omega s. This is called sampling frequency. And Ts is called sampling period. So P of omega equal to sigma k equal to minus infinity to plus infinity. So 2 pi over Ts del of omega minus k times of omega s. So this is continuous time Fourier transform of your rectangular rectangular impulse train. Okay, so these are required for me to discuss sampling. That's why I discussed before going to discuss sampling. Okay, now I'll come to sampling. What is sampling? Sampling. Okay, I'm not saying sampling theorem. I'm just saying sampling is a process to convert continuous time signal into discrete time signal. Okay, what a sampling theorem means, once you convert this continuous time signal to discrete time signal, can I reconstruct the original signal from the discrete version of the signal to continuous time signal? Can I reconstruct? If it is possible to reconstruct, what is the condition. That condition is nothing but Nyquist criterion. Okay, so we'll discuss anyway. So we have a block continuous to discrete block. We have, let us say, XCFT. XCFT means continuous time signal. X of n. This block will convert continuous time signal to discrete time signal. This is called sampling block. Okay. So this has a parameter Ts, which is sampling period, sampling duration. Okay. So what I have to do? First, I will represent graphically all these things. If I have XCFT as like this, continuous time signal, like this. Okay, I want discretize this XCFT. So then I will multiply with this impulse train. This is my impulse train PFT. It has time period Ts, 2Ts, 3Ts, minus Ts, minus 2Ts, minus 3Ts, and so on. Okay, this is my PFT. So what I have to do is I will just multiply these two signals XCFT into PFT. What I get? Let us say XSFT, XCFT into PFT. What I get? 0 Ts, 2 Ts, 3 Ts, minus Ts, minus 2 Ts, minus 3 Ts, and so on. So here the values, here the values are x of 0, here x of Ts, here x of 2 Ts, x of 3 Ts, x of 4 Ts, x of minus Ts, x of minus 2 Ts, x of minus 3 Ts, and so on. Okay, so this is still in time domain t. All these are in time domain. Okay, so what I got? I have lost information from here to here. what information I have lost? 0 to ts. In between, whatever the information initially I have, that I have lost. Yeah, 0 to, let us say, ts. So this information I have lost. Okay. Okay. So yeah, I have lost information. Can I recover the original signal from this XS of t? Can I recover? Yes, you can recover. Under what conditions? So that is nothing but your Nyquist criterion. Anyway, we will discuss. And but still, it is in time domain t, continuous time domain. I want a discrete time signal. So discrete time signal means discrete time signal means your axis is not t, your axis is n sequences. Okay. So what I have to do? This is n. What I do? So these are the sample I have, and the sample values also x of ts, x of 2ts, x of 3ts, x of 4ts, and so on. This is x of 0, x of minus ts, x of minus 2ts, x of minus 3ts. And what I will change is 0, 0 to 0, ts to, I will map 1, 2ts to 2, 3ts to 3, 4, 5, minus 1, minus 2, minus 3, and so on. So now it is in discrete time. Now it is in discrete domain, but of course it is discrete domain, but here these signals are impulse signals. Okay, so your axis is discrete only, but we are representing these as impulses. So what I have to represent them? I have to represent them in terms of stems. Okay, so I will replace these impulses with stems. Okay, so okay, I will try again. I don't want to disturb this. I'll draw again. This is n. These are stems. Will represent discrete time signal as stem plot. So these values are 0, 1, 2, 3, 4, 5, and so on. Minus 1, minus 2, minus 3, and so on. So now this is exactly discrete time signal. Okay. So I will represent this as x of n. Okay. This is excess of t. This is excess of t. Okay. So from excess of t to x of n. From excess of t to x of n. Have I lost information? No, I have not lost any information here because the values are same. So here this is x of 0 only, this is x of ts only, this is x of 2ts, x of 3ts, x of 4ts, x of minus ts, x of minus 2ts, x of minus 3ts. Only the difference is here to here. Here x of 4ts means this is area of this impulse. Area of this impulse. So here 0, x of 0 means this is area of this impulse. But here x of 0 means this is not area, this is strength of this sample. This is x of ts means the strength of this sample. Okay, that is the only difference. Have I lost any information from here to here? This is just a conceptual jump from xs of t to x of n. I have not lost any information. I just mapped this time axis to sequence n axis, ts to 1, 2ts to 2, 3ts to 3, and so on. Okay, and these impulses are replaced by the stems, but the values are not changed. Okay, and here I want to declare some points regarding the representations. So I will reserve these curved brackets to continuous throughout the methods. I will reserve these curved brackets to continuous case, and I will reserve this uh, square brackets to discrete. Okay, so this is like a book notation. Okay, if you follow Oppenheim and Schaeffer, so you will see these kind of notations. So that's why I'm following these notations. And so x of omega, this is capital omega. I'll say capital omega. So I will reserve this symbol for continuous time frequency, and x of e power j omega, this is little omega, small omega. I will reserve this symbol for a discrete time frequency. Okay, so what do I mean continuous time frequency and discrete time frequency? Continuous time frequency means the frequency of continuous time signal. Okay, for continuous time signal we have Fourier representation is CTFT. I will represent this capital omega. For discrete time sequences I have Fourier representation is DTFT, that is x of e power j omega. Okay, so these are just notations so that you will not confuse throughout the course. Okay, here I want to discuss some more things. The frequency domain representations here. This is XCFT. I want to represent them in frequency domain here. Okay, what I have to do to know the frequency domain, frequency components present in these time domain signals. Okay, so what I have to do, what transform I have to apply. This is in time domain, continuous time domain. and the signal is not periodic. Okay, then we have to apply CTFT, continuous time Fourier transform. I will come to all these things when I discuss uh, from the basics. Okay, welcome. Next, PFT. We already found CTFT. This is periodic signal, so you can also find CTFS, continuous time Fourier series, because it is periodic signal. Excess of t. This is not periodic, so you have to find CTFT. This is also excess of t. Just wrote 2 times. And this is my interest. What I have to do here? This is not x of t. It is not in continuous time. This is in discrete time. X of n. So we have to find out dt of t. Okay, this is important. Okay, so xs of t to x of n, we have not lost any information. So both are same, xs of t and x of n. But xs of t has frequency domain representation as CTFT, and x of n has frequency domain representation DTFT. So from these two, we can derive a relation between continuous time Fourier transform and a discrete time Fourier transform. Okay, that is also important. Okay, I will derive each and everything in the next lecture. So I'm going to stop. Okay, thank you.